2.
Buenas tardes a todos. Hoy 12 de octubre del 2021 daremos comienzo a la quinta sesión del ciclo de conferencias del Dr. Peter Molnar. Bienvenidos otra vez. Peter, how are you? Welcome again to
I'm very well.
The auditorium is waiting for you. Go ahead.
Thank you. Thank you, Hector. Okay, today I will talk about vertically averaged, should say, lithospheric rheology. And the main topic that underlies are continents so different from oceans or oceanic lithosphere where plate tectonics works well. And just, we were looking at this photo before the rest of you joined. This is the surface rupture from a very large earthquake, Gobi Altai earthquake, 1957 in Mongolia. So you see two friends here, Bayaskalan and Engtufshin up here. This is just a spectacular surface rupture. This photo was taken in 1993, so 36 years after the earthquake. Okay, just to show you again the seismicity map of the world. And you all know that narrow zones are plate boundaries, and what I want to focus on is the diffuse seismicity in continents. So narrow zones through the Mid-Atlantic Ridge, through the East Pacific Rise, through the southeast Indian branch of the Mid-Ocean Ridge, along the Aleutians, along the Mariana Arcs. These narrow boundaries are plate boundaries, but when one goes into continents like the Western United States, like Eastern Asia or Western Asia, earthquakes are scattered all over. This is a map of earthquakes, and they're scattered all over. So instead of narrow boundaries, we have widely distributed deformation. And this, I think, is the first clue that continents are different from oceans. Here's a map of GPS velocities, a recent map just last year, relative to Eurasia. So everything is relative to Siberia up in here. And you see the velocities point north-northeast in here, but everything swings around. And I think you would take this pattern and you would not describe it as blocks, but you'd describe it as flow. There's flow of crust. There are some blocks in here, a couple of big ones, Trim Bay and Rhodos block. But you don't see evidence of plates. You see just this continuous deformation. And if you blow up the Tibetan area, it's the same. Just this flow around the corner, around the edge of the Himalaya in here, flow out to the westward. This is behaving as a rigid block. Now, this hasn't stopped people from interpreting the deformation in terms of blocks. And so the first part of what I want to talk about is how I think they're wrong. So here's one example of blocks. So the Himalaya would lie down here. This would be the Tibetan Plateau, big major fault, the Altantag Fault, coming across here. With these slip rates, they're wrong, I think. But the most glaring example is a slip rate where this fault, the Shenshui-He fault, is shown to have a 20 millimeter a year rate. And we know from geology and geodesy that it's only about 10 millimeters in here. So as soon as blocks are introduced, mistakes are introduced. And here's another one, different author, different paper. Again, this is that same Shenshui-He fault. It's a strike slip fault with a slip rate, not 15, but 10 millimeters a year. And this is showing with these oblique directions of relative motion. It's simply wrong. And to get this right means adding some blocks. I want to focus in as an example this area up in here. And if we go into this area that I pointed out, or this area in this on this map from blocks, and here's a topographic map. Northeastern Tibet lies down here. There's a big fault, the Kunlun Fault, coming across through here, but there are a couple of faults that are smaller. The Ulashon Fault, shown as a line through here, you see in the topography, and the Ulashon Fault, this one over here. Now, the Ulashon Fault is shown on this map with, in this case, a 3 millimeter a year rate along the fault. Here is shown on this map as a 6 millimeter a year rate. I'm going to tell you that it's only 1 millimeter a year. And the Ulashon Fault is not included at all. There's no fault shown, no fault in this area. And I'm not going to show you the evidence for the rate, but I'm going to try to hone in and show you that there's no question about there being one of these faults, and the other is quite convincing too. So the Elashan Fault is here. The Ulashon Fault goes up there. So you can see this in the topography. Again, same thing. This is a lake in here, Qinghai Lake, and this is a mountain range that's actively growing through here, but this is our Ulashon Fault. If we blow that up, we look at this area and look at a geologic map that comes through here. In this area, you see a beautiful offset. Granite, this Paleozoic granite, it's been displaced 8 kilometers from this block of that granite. The fault, of course, runs along this boundary between them. This is an old geologic map. They weren't looking at active faults, but there's no question that there's a fault through here. We can see this today, and there's no question there's this offset. And if we take this site and blow it up, here's a blow up of this region in here, and you can see in the topography this nice line coming across through here. This is an active fault, this beautiful example in the topography. And if this red box, we blow that up to show you this region, you see here's this fan-like feature, that feature in here, with a very clear escarpment coming through here in this area, and going through this line right there is the fault. It's easily traced. We see a hint of offset in here. We worked in this area. I know this area quite well. I'm not going to show you the data, but I will say that we got a slip rate of 1 millimeter a year on the Ulashon Fault. And this is quite tight, 1 plus or minus a few tenths of a millimeter. Not 3 millimeters a year as one block model had, and certainly not 6 millimeters a year. And moreover, the Ulashon Fault over here, again, one gets about 1 millimeter a year, not 0 as those block models had before. So I would argue that active regions are littered with faults with low slip rates, and with yet more faults that are still more minor, and ultimately we get to grains of sand. So one has faults, one has many, many faults, and if you treat these as blocks, it's an endless process of making more and more blocks. And here's my way of looking at this. If we had big N GPS points, we would have little n blocks, and the value of n will vary as big N raised to a power, therefore fractally, where the power is less than 1. The power is a positive number, but it's less than 1. And so the more GPS points we get, the bigger the n. That means we have more blocks, and this goes on ad nauseum. We don't get anywhere with this. Now, if we go back to what was the key to plate tectonics was recognized arguably in 1965 or 1967 or 1968. One of the key players was Dan McKenzie, and McKenzie wrote, "The great success of plate tectonics came about because it separated the problem of the kinematic motions from that of the driving mechanism." And if you think about the ocean or the atmosphere, you can't predict the kinematics without knowing the dynamics. It's simply impossible because there are balances of forces continually at work. So the success with the kinematics, the success of plate tectonics came because we didn't have to know the forces that were acting. We could just see plate tectonics in action. And no separation or simplification can be made for continental tectonics. It's just more complicated, though not terribly complicated. And the key is that continental regions, I argue, deform as continuous media. A key to that is gravity resists the deformation. Gravity does not play a role in the resistance of plate motions. And so the kinematics and the dynamics are inextricably linked. One can't separate one from the other. I should say at this point that this is my opinion. This is not necessarily I'm wrong, or I'm certainly wrong in some ways. and many people disagree, but this is the philosophy with which I'm bringing to what I'm telling you. And so let's look at this in yet another way. This is a painting by Camille Pissarro, back 1898, Rue de l'Épicerie in Rouen, France. This is the Street of Spices, and it's clear that's the Street of Spices going through here. And if you look at this, it's clear there are lots and lots of people. It's a street full of people. There's no question about it. But if you take part of this picture and you blow it up, as I've done over here, well, yeah, you can see the people in here. You can make them out, but let's blow a bit more up. Let's blow that part up. And if you blow this part up, you'd never see people. If this is just strokes of paint that Pissarro has put in, and he's put it in a beautiful way. He's done this in this area so that it looks like people. Obviously, he's done something else. So I'm using this as an impressionist painting as an analogy for continental tectonics. For some questions, we must examine the small scale, and for some, the large scale. But scaling up from the small to the large requires that we understand the phenomena that link them at the different scales. And understanding, this is the key word. The key word that McKinsey used to say that plate tectonics worked because we did not need to understand how we scaled up. We just had the kinematics. So one last analogy. I see blocks as one way of approaching GPS and crustal deformation, and continuous deformation is the other. And to me, they're like the Ptolemaic system for where the stars are in the sky, the tables that Ptolemy, the Greek, compiled long ago, versus the Copernicus, Kepler, and Newton system. Copernicus with the sun at the center, Kepler with his three laws, Newton with gravitation that held those together. If you were a sea captain at the time that Copernicus proposed that the sun was the center of the solar system and not the Earth, and you were a sea captain, you would not have used what Copernicus proposed. You would have used the Ptolemaic system because it was accurate, just as blocks can be accurate. But if we want to understand, Ptolemy doesn't help us to understand. We had to go from Copernicus to Kepler to Newton to understand, and I would argue we need continuous deformation to understand continental tectonics, continental deformation. Blocks can provide a description, but it's a dead end when you get there. Okay, where does the strength in the lithosphere lie? This is a simple profile going through, and this is drawn for oceanic lithosphere. So there's a thin crust at the top. Water is what would lie above here, plotting depth versus strength. And the strength increases with depth, we assume, because of friction. Friction, the rule for friction is the shear stress is equal to a coefficient of friction, mu. Mu is the coefficient of friction, times the difference between the normal stress and the pore pressure. Pore pressure can push the sides of two blocks apart a little bit and reduce the normal stress. So this is the effective stress. The normal stress is, we can look at it as the lithostatic pressure, and this increases with depth. This simple picture works for the brittle part. And then when one gets deep enough, the Earth becomes hot enough that instead of brittle deformation, we have viscous or plastic deformation. Temperature increases with depth. The strength decreases with increasing strength. And so we have a curve that plots something like this. This is now going to the data, normal stress versus shear stress. So it's a plot of this equation where there is no pore pressure in these cases. These are data from various different kinds of rock. I took this from a paper by Byerly. Others named this Byerly's law. And the data fit on a quite nice straight line. The shear stress is proportional to the normal stress with a coefficient of friction, in this case, 0.85. This is the case. I'll give you a deviation from a little bit in a second here. All of these, or most of these measurements, were made by putting rocks in machines in a laboratory and sliding one side past the other. And usually the kind of deformation one found in this is called stick slip. So one loaded the system and then all of a sudden there would be slip, abrupt slip, and then it would stick together again. And then if you kept loading, it would slip again, much the way earthquakes occur. And this process, stick slip, has been likened to earthquakes. It's an analogy that was made 50 years ago and still holds well. But there's a deceptive part of this. So if we have low temperature, we have stick slip. So this is a plot, temperature on this axis, 200, 400, 600 degrees Celsius, and shear stress here with the normal stress being held constant. And when you're cold, you have stick slip and you have data that lie up in here. But when you increase the temperature, you don't weaken the material very much in this temperature range. Instead, you transform from stick slip to stable sliding. So in other words, you're sliding the two rocks past one another. When it's cold, this happens with jerks. The sticks and then slip. The stick, it doesn't slip, and then it slips abruptly, and then it stops, and so forth. Whereas when you move into this area, it slides at essentially a constant rate. And if you plot now shear stress on this axis versus normal stress, plot data, all of these data against shear stress against normal stress, most of the data fall on a line, and temperature is irrelevant. Some are 25 degrees C, these big circles are 25 degrees C like those. These black squares, which occur right next to them, are much hotter, 500 degrees C. And even these small circles at 600 degrees C, these small circles in here, they all fall on the same line. The difference between experiments at different temperatures is not the coefficient of friction. It's whether slip is abrupt or whether it's a steady, stable process, stable sliding versus stick slip. And when you get to 700 degrees, okay, maybe the data begin to deviate. So if one looks again at this picture I showed before, it was a little bit deceptive. I'm going to go back to the simple pictures further on. But when we're at shallow depths or low normal stresses in here, one has velocity weakening is stick slip. Another way of saying this is the coefficient of friction in this area. The coefficient of dynamic friction when slip is occurring is lower than the coefficient of static friction. And I think you all know this. If you take a spring and attach it to a piece of wood and drag it on the floor, it won't be steady, at least if you are slow, it will occur in jerks. And those are where the earthquakes occur. But faulting continues to greater depth. As one goes down, faulting occurs. There's stable sliding in this region. In the laboratory, this would be stable sliding. The coefficient of friction may be decreasing a little bit. But in this region, there's still slip-on faults. Velocity strengthening means there's steady slip. As you slip faster, you get more resistance, but you don't stop. Until finally one reaches the plastic creep down in this area. And when you're in this region, when we're at the depth where plastic flow occurs, faulting has stopped. Deformation is continuous in this region. Up in here, we have faults, we have blocks, we have little blocks of various sizes, but when you're down in this region, it's continuous deformation. And the argument that I was making before is that the average of all of this is more like plastic deformation, more like continuous deformation than like with faults. And of course, the steady creep rate, it increases with stress, but also with temperature. So as the temperature goes down, goes up, the resistance goes down. Okay, if we use equations to describe this, when we're at high temperature and moderate stress, not the highest stress, what's known as dislocation creep occurs. Epsilon dot is the strain rate. It's proportional to some constant times an exponential, where the exponential depends on temperature. It's usually written in this form. The H in the numerator is the activation enthalpy. So if this is a big number, if this is a big number, you'll get a different temperature dependence on the strain rate from the and the stress strain rate relationship. This is a big number for olivine, which is strong. It's a smaller number for quartz, for example. R is the ideal gas constant. This arises because of the thermodynamics that's involved. T is temperature, but in kelvins, of course, not in degrees Celsius. And then stress, this is stress difference, shear stress or deviatoric stress. It's twice the maximum shear stress, raised to a power n. And for most rock-forming minerals, like quartz, like feldspar, like pyroxene, like olivine, n is a number in the range of 3 to 3.5, in that range. This works quite well. There is a range where n can be 1, which is very simple. I will talk about this a little bit, but that's not a condition that applies very much to the lithosphere. It applies mostly when temperatures are high. I'll come back to that. Now, if you go to lower temperature and higher stress, what we have is something called Peierls creep. Peierls was a Russian physicist who emigrated to Paris, to France, back in the early 20th century. And this equation this is a messy equation. This is written in different ways. And so I've collapsed a bunch of different ways into one here. But the strain rate will vary, again, with some constant. There will be a stress term in here raised to this power R. In early studies, R was 0. So this term would be vanished. But to the 0, of course, would be just 1. Now people are saying maybe that number is a little bigger. Then you have, again, this exponential with an activation enthalpy and with a temperature in the denominator. And let me point out that as the temperature decreases, this number becomes bigger, but it's a negative number. And so as you make this number bigger, as you decrease the temperature, this becomes bigger, but because it's negative, the strain rate becomes smaller. It makes sense that if you make temperature lower, the strain rate will be smaller for a given stress. And the negative takes that into account. But then you have this factor that multiplies the exponent, this exponent, and it includes stress again divided by some constant, this sigma E, raised to a power P. In the old days, this was 1, but now we see this number sometimes given as 0.5. And then this term raised to some power Q, and that's usually a squared term in here. But if you look at this, you can imagine that when sigma is small, when that's a small number, and this is a small number, the strain rate should vary weakly with the stress because this won't change very much. That's true. But more interesting is that when sigma approaches sigma E, in other words, when this number gets close to 1, this factor, 1 minus a number almost 1, this goes to 0, and then there's essentially no temperature dependence. This becomes independent of temperature because this factor is nearly 0. If this sigma over sigma E were equal to 1, this would be 0, and then there'd be no factor in here, there'd be no dependence on temperature at all. And for a perfectly plastic material, no strain occurs until the maximum shear stress is reached at a yield stress, and then strain occurs at a constant rate. Well, that's what you might expect in this case, with this independence of temperature. Well, if we plot these are just some examples for 3 cases. This is recent work by 2 different orientations of crystal planes with slip in those planes with different orientations, or the red and the black, and then a case where the olivine has been hydrated. The hydrated one is weaker, but let's just look at this. This is if we have a constant stress here, sigma, either in this or in this equation, it's held fixed. So we look only at the strain rate as a function of temperature. Strain rate is a function of temperature. Indeed, as the temperature increases, the strain rate increases. Here, this is log 10 of strain rate in per second. So 3 times 10 to the minus 8th would be per year. This would be a strain rate once per year. So we're getting fast up in here and slow, but you can see a huge range of strain rates, with strain rates increasing with temperature for a fixed value of the stress. Over here, what's fixed instead is temperature, 3 curves, 3 different temperatures, 800, 700, and 600 degrees C. Of course, in these plots, temperature is written in kelvins, but we think in Celsius. And of course, when it's hotter, the strain rates are faster. These are log 10, and they're relative numbers. So this is a much faster rate of strain than these numbers down here. And indeed, when it's cold, it's slower. As the stress gets bigger, the dependence on the temperature gets smaller, and the dependence on the stress flattens out and becomes quite small. This is this plastic behavior that I was mentioning, where for a given temperature, the strength doesn't depend very much on the stress at all, whereas here is a very strong stress dependence. And you see that also that these curves are very different from one another. The hydrated curve is much weaker, strains much more rapidly for a given stress, given temperature, than for the other two that are not hydrated. The uncertainties in this applied to the Earth remain large. If we look at oceanic lithosphere and intraplate Earth, this shows this in a nice way, shows another aspect of in a nice way. Let's take the bottom of these plots. This is the age of the oceanic lithosphere from 0 at the ocean ridge to 150 million years. And these are estimated temperatures as a function of depth on this axis at different ages. So 1200, 1300 degrees C down here. And the earthquakes are confined to 600 degrees Celsius. This is a very nice, well-defined number, very nice defined quantity here. 600 degrees is close to the cutoff. If you're colder, you have earthquakes, you have brittle deformation. If you're warmer, you have ductile deformation. And if you blow up this corner of younger than 4 million years, so here's age out to 40, depths coming down here, again, the 600 degree isotherm does a good job of bounding where the earthquakes occur. A couple that might be deeper, but not very many. If you step back from that, those are cases where it's cold 100 degrees, and they're intraplate, and they're within where strain rates are very small. Intraplate is a, by definition, very low strain rates. But we have other places. This Wyoming case, I'll come to that in a minute, actually. We have other places where we think the strain rates are larger and where the temperatures we think are higher, estimating the temperatures. And these blue, red, and black curves are curves for a fixed stress, fixed stress difference or maximum shear stress for those 3 curves before, those 3 laboratory numbers that I showed before. And plotted here then is temperature going up. And when you get very hot, out to 1200 degrees C, you can actually get earthquakes. You still have brittle deformation at strain rates that are quite high, strain rates that are the order of 1% per year. This is really rapid deformation. So the brittle ductile, the boundary between them was to depend on temperature, also depends on strain rate. Where we go from brittle to ductile is not a fixed number. It's not set at 600 degrees as it is in intraplate settings, but it varies with temperature and strain rate. Now, we can look at this in another way. This is a very nice summary by Bergman and Dresen 15 years ago. And they've made a plot now, differential stress on this axis, where they've fixed the strain rate. They're using this same basic equation that we've been using all along for high temperature creep. strain rate goes as some constant, an exponential of an activational enthalpy divided by temperature times stress to some power. But what they're looking at here is grain size. I mentioned this a little bit earlier. If you have small grains, the deformation can occur by diffusion of atoms or vacancies within a crystal, and that can be grain size dependent. You're diffusing through the crystals, and if the grains are small, you can diffuse to the edges and cause deformation more quickly than if the grains are larger. And in this region, the value of n is 1 in this range, but there is a term for strain rate dependence in here. If you get to the high temperature creep, where n is 3, then this is a straight line across here because grain size, it's independent of grain size, and it depends on this strain rate. But you can see the temperature dependence plotted here is the effective viscosity in Pascal seconds, the differential stress. So stresses increase in this direction, viscosity in this direction, and that happens as you get colder, as you go colder and colder. I'm not worrying about the diffusion creep because in the crust, you're almost never as cold, as hot, I should say, as 600 or 700 or 800 degrees C. That's a very hot crust. And in the mantle, when you get to these temperatures, you're still usually in the lithosphere, you're in the high strength region where this equation may not even be the right equation. If we look at, there we go. If we look at this for minerals, I've just shown you the case for wet quartz over here. And we compare them for wet quartz. So here's 500 degrees C, here's 10 to the 20th Pascal seconds for the viscosity. If we take 10 to the 19th as a nice number to look at, that occurs 10 to 19th Pascal seconds. This is an asthenospheric viscosity or a low viscosity. If you're at 700 degrees C with quartz, this is quartz, you're there. A little stronger. To get to 10 to the 19th Pascal seconds, you need to have 800 degrees Celsius. So it's a little hotter. But olivine, it's 1,000 degrees Celsius. These numbers I'm being approximate. But olivine, you're just simply much stronger than you are with quartz or feldspar. In order to reach a stress that's viscosity, you have to make it pretty hot. And if you were at 700 degrees C with olivine, you'd be way up the top here. You'd have a viscosity that would be extremely large, ridiculously large. What that means? That means that if you go to continents where quartz and feldspars are dominant minerals, the crust is much weaker than the mantle is. This is the plot for oceanic lithosphere, and we haven't worried about the effect of the corner in here. Quartz, you're coming down in the brittle deformation, but quartz, when it becomes hot enough, you become ductile and the crust becomes weak. It's possible that the lower crust where pyroxenes are present, I should say that pyroxenes, wet pyroxene in particular, even wet pyroxene, is stronger than olivine. So it's possible that the lower crust with some fraction of pyroxene could be strong, and stronger definitely than the upper crust. So this part of this curve is meant to indicate that. But the point here is that you've got this much weaker zone, whereas in the oceanic domain, you don't have that. You have pure olivine, and olivine is much stronger than quartz or feldspar. So you take this gouge out of the strength curve. You much weaker. The integrated strength of this is much smaller than the integrated strength in this case. And hence, this, I think, and I may be unusual in thinking this, the reason plate tectonics does not work in continents is you don't have the strength that you have in oceanic lithosphere. You have this strong core of olivine, which maintains a plate, whereas with continental lithosphere, the crust can slide relative to the mantle. You can detach layers in this region, and the behavior of the mantle can not be independent of the crust, but can be separate from it and deform differently because of this weak zone. You just don't have the strength. This plot shows that the brittle deformation would reach the ductile before you got to the moho, but you can imagine a place where the crust might be thinner, or a place where you'd be colder, and in either case you could have more brittle deformation in the mantle. And I'm going to show you an example of that, a couple of examples of that, because I think this is important. And this comes from studying earthquakes. This is an intermediate depth earthquake, a depth at 90 kilometers in Tibet, beneath southern Tibet. This is the lower hemisphere diagram of the fault plane solution. So think of this as a stereographic projection looking down. That's the bottom. That's looking straight down toward the center of the Earth, north, east, south, and west. And each of these points then, that's a point that radiated, that shows where a seismogram was recorded out to the northwest at some distance. And because this is a normal fault, this would have had a first motion that is upward. You don't see it very well, but that would be upward. And plotted here are seismograms, and both seismograms and synthetic seismograms. So beneath each one, you have a recorded seismogram and then a synthetic seismogram shown over here. And for each one, you can see three phases: a P wave, in the synthetic P wave in here. The little p, big P, this is the P wave that is reflected off the surface of the Earth. This P wave, the first arriving P wave, comes straight, radiates downward from the earthquake and goes far away. This P wave radiates upward, reflects off the surface of the Earth, and then goes down. And then the little SP was an S wave that went from the earthquake up to the surface, reflected off, converting to a P wave, becoming a P wave, and going off to a distant station. And the time between the P and the PP or the SP, that tells you how deep the earthquake is. And so these are some examples of P waves. P waves are weak, but the little p, big P is strong. The little SP is strong. Again, you don't see the P waves very well. That one a little better. There's the direct P. Here you barely see the little p, big P, and there's the SP. And that time interval, there's a minute. That's a long time between them. That allows the depth of 90 kilometers to be determined. Now, the reason this is interesting, I think, is that if you look at the depth distribution of earthquakes, this is a plot of, first of all, this is a map of Tibet. So the Himalaya lie down here. These two earthquakes, one of those earthquakes I looked at, that I showed you the seismograms, is this one. There's another one that we studied that's down in here. So this is a map of the Tibetan Plateau. And if you plot longitude on this axis and depth on this axis, you have most earthquakes are in the upper 10 kilometers. This is just going down 10 kilometers, but you have these deeper ones down that are in the mantle underneath, and this aseismic region in between. And I emphasize that the fault plane solutions of these deep earthquakes, these two at 85 and 90 kilometers, are similar to the shallow earthquakes. So they're telling you that the style of deformation at depth is no different from the style of deformation up here, as if this all connected, except that you probably have a weak zone that cannot support earthquakes in the middle and lower crust under Tibet. Now, this is quite old. This is almost 40 years old, but subsequent studies have added many more earthquakes. So here's a profile. There's a map showing where some of this is. Again, the Tibetan Plateau in this region, the Himalaya lying down along in here, and a profile. The Ganga Basin, which we talked about last week, with the Himalaya coming across, and then into the Tibetan Plateau. The suture between the two, between India and southern Tibet, lies right in here. And again, now they have many earthquakes that are occurring down in this area. The Moho, this is one version of the Moho. This is another version of the Moho, but these earthquakes are below it. And here's the Moho in a seismic reflection profile. Again, earthquakes below it. So this is not a rare phenomenon. on. This where you have shallow earthquakes that are in the crust as well, but with a region between with not many earthquakes. That's not necessarily the case, but that is the case. And let me show you another interesting example. It's a little bit different. This is now the East African Rift. So Ethiopia is up here, Kenya would lie in here. This is Lake Victoria, Lake Tanganyika, Lake Malawi. We're going to look at this region that's blown up in this picture and look at this earthquake. And here's the P wave. Here's a time scale, 10 seconds. So this is the P wave to some distant station. This is the little p, big P, the P wave that's reflected off the Earth's surface, or actually maybe off water surface in here. This is a synthetic seismogram. This is the recorded seismogram. Again, same thing, P and the little p, little p, big P. But what Yang and Chen have focused on is this little phase that comes after the P wave. This phase right in here. This is the synthetic. This, as you see in here. And this little phase is, they argue, then the synthetics use this argument, this is the phase that is reflected by the MOHO, from the P waves. So this is, so the P wave here went down to a distant station. The little p, big P went up, reflected off the Earth's surface, and then to a distant station. But this phase was a P wave that went up, reflected at the MOHO. The MOHO, of course, the impedance contrast at the MOHO is much smaller than at the Earth's surface, so you get a much weaker reflected signal. That's the synthetic of this. And this is telling you that this earthquake occurred in the mantle. And they estimate a depth of 44 kilometers for the depth of the earthquake, and the MOHO at only 32 kilometers under the Rift Valley in here. But the point here, again, there are subcrustal earthquakes in this region below the MOHO. And this is the fault plane showing normal faulting again. This one was studied by Germán Prieto, one of your colleagues. From western Wyoming, the location of the earthquake is right here. This is the Yellowstone area, a high, hot region. This is a this is a map showing the S-wave speeds in the mantle around the depth of the earthquake. The blue showing high speeds greater than 4.6 kilometers per second. This is typical of cold shields. And then the red showing lower speeds under Yellowstone in that area where speeds are getting down to 4.2 kilometers per second. And the earthquake in a profile, A prime, occurs at the edge of this cold material, not terribly cold, but at the edge in here. And again, if one looks, here's the P wave, and this is the little p, big P reflected off the surface, and the red is the synthetic, and the line underneath is the original seismogram that was used to match these. And then a plot of residuals of between synthetic seismograms and recorded seismograms, as the residuals here is a misfit as a function of depth, and the earthquake's at 75 or 80 kilometers deep underneath this region, 75 kilometers underneath a region where the crust is only 30 or 40 kilometers thick, probably. So once again, an earthquake in the mantle well below the crust. And so we have at least two cartoon images of the strength profile. The first on the left, this is the one that I've been showing you first. It's called the jelly sandwich. You imagine a piece of bread with jelly inside, which flows, and then another piece of bread. So the top piece of bread would be the upper crust. The bottom piece of bread would be the upper mantle. You have a lower crust, for instance, wet quartz, brittle deformation to here, then weak because it's wet quartz or wet feldspar. Then jumping up because the mantle is much stronger, dry olivine, you could even have brittle deformation in here where you would have earthquakes, even possibly earthquakes in this area. But if the region's really hot, then you get something that might be more like creme brulee, where the depth of the brittle layer is shallower. You come down, you intersect wet quartz in here at a shallower depth, so you have a thick layer of weak lower crust. Maybe you even have dry feldspar, which would make it strong, but it doesn't matter. And because the mantle is hotter, this curve then the temperature at this depth, let's say 35 kilometers, in this case is quite low. In this case, the temperature at 35 kilometers is much hotter, so you're weaker. You have a brittle layer on the top. It's like the part that's been heated, brûlé means heated, and then it's a soft material underneath. They have a third one, a banana split, which I haven't included in here. But this image came about in part because of the earthquakes, with the gap in the earthquakes, shallow earthquakes, no earthquakes, and then earthquakes within the mantle in some regions, but not in all regions. Okay, I want to change directions and, oh my God, I'm running low on time. Change directions and go to another topic, which is why do we have major strike slip faults where we do? And I hypothesize they form adjacent to regions with strong lithosphere, and they separate deforming regions from these strong regions. And if we go back to this expression for strain rate as a function of stress, here I've written it as shear stress. What we'd like to do is invert this and write stress in terms of strain rate. There's a trick that has to be played to get there, especially if we want to do this realizing that strain rates and stresses are tensors. And if we invert this equation, of course, then the stress can be written in terms of, instead of an A, we have a B. And the exponent, we take the nth root of this, so we have HD, now nRT, and we get rid of the minus sign because we move that to the other side, right? We're writing stress in terms of strain rate, so we move that to the other side. But how do we take care of this? And the way this is usually done is one uses what's called the second invariant of the strain rate tensor, which is this ugly quantity right here. The three shear stresses, three principal shear stresses, or three shear stresses, the three products of the three normal stresses in this way. We raise that to a power, and now this power, of course, 1 over n minus 1 is a negative power. We multiply that by epsilon dot here to the first power, and we effectively get the nth root. If we just took the nth root of this side, we would have strain rate to the 1 over n power, but we have to have a tensor to make this work. And I want to consider a strike slip fault where the strike slip faulting is in the YZ plane, so it's parallel to the y-axis, and we're going to be looking at phenomena in the x direction with that orientation. But in this case, the y component of slip in the XY plane in here clearly makes the shear stress tau XY important. This is the shear stress is important here. The normal stress in the XY plane parallel to this axis, a normal stress oriented this way, is not likely to be important, and let's just ignore it. And let's also assume that shear on horizontal planes and parallel to the y-axis is also negligible. That is a negligible quantity. The reason for doing this is if we go to the equation of equilibrium, but we're going to look in a horizontal plane, so this quantity, the body force, is 0, z points down, we're looking in the xy plane, we have only one quantity, one of these three equations we need care about, and that's the gradient in the shear stress in the x direction plus this gradient of the y normal stress in the y direction plus this gradient in the vertical of this tau yz direction. Well, we've assumed that this is unimportant, that this stress doesn't, if it's there, it doesn't vary in the y direction. And we've assumed that this isn't important. We wind up with this very simple equation. And that simple equation, that shear stress does not vary in the x direction, means that this shear stress is a constant. This is a simple equation. If you have a shear stress that's constant, you might quit. But let's go a little bit further. And the reason we can go further is we can now worry about non-Newtonian viscosity where n is not equal to 1. because we're starting with the shear stress being constant, but we have only one component of strain rate, only one component. That's the only one of 6 possible components of strain rate. And what that means is that the second invariant is simply that component. We have this equality. I'm putting it as not exactly equal because we're going to let the shear stress vary, the shear stress, the tau xy, in the x direction. So this isn't quite exactly equality, but close enough. If we put that into this equation, then our shear stress is simply our viscosity coefficient times that single shear stress to the 1 over nth power, or to the nth root in this case. So now let's let the shear stress vary gradually, but linearly for simplicity, with distance, with only one component of strain rate. So in other words, our shear stress is a maximum where x is 0 and decreases as x gets larger and larger towards x0, where then it vanishes. If we have this expression, tau equal to this, and we invert this, our shear strain rate, which is our shear stress to this nth power, is this tau max here to the nth power. I've left out the b. I'm sorry. The b should be in here. I've left that out. And then with this 1 minus x over x0 to the nth power, but now with that nth power, that's a big effect. If we plot this, this is now from 0 to 1, where this can be the shear stress or strain rate as a function of distance x over x0. Our shear stress decreases linearly, but our strain rate, if n equals 3, follows this blue line. And if n equals 10, it follows this red line. And what this means is the strain is much more concentrated near x equals 0 when n is larger and larger. That's the point of where I'm going. So if we again go back to this linearly decreasing shear stress, the strain rate doesn't decrease linearly. It has this nth power. So tau xy decreases to half at a half x0. If we put x equal to a half x0, 1 minus a half is a half. But the strain rate at a half will then be 1/8, because 1/2 to the third power is 1/8. This is 1/8. And for n equals 10, the strain rate is decreased to a half at only this negligible distance. It's hardly gone anywhere. And so the hypothesis is that major strike-slip faults form adjacent to regions with strong lithosphere, and hence they separate deforming regions from these strong regions. And I'm going to take you on a tour of, and I'm going to skip a couple because I'm too far behind. But look at a few examples of major strike-slip faults. These red lines show you faults with slip rates of at least 10 millimeters per year. These are the major faults by that definition. And if we look at the North Anatolian Fault in Turkey, with a slip rate of nearly 20 millimeters a year through here, Red Sea, the Black Sea, this area has strong oceanic lithosphere underlying it. And so it has a strong region next to it with deforming continental lithosphere next to it. So it's at the boundary. The fault is bounded to the north by the Black Sea, which is underlain by this old, cold, strong oceanic lithosphere. It's near that boundary. The San Andreas Fault, which comes down through here and has a quite high slip rate, we're getting up to 30 or 35 millimeters a year. This is almost a plate boundary. The Pacific plate is strong out here to the west. And in fact, the Sierra Nevada may be strong. But this is bounded by a strong plate. The Fairweather Fault, this fault is again, this is the fastest strike-slip fault on land in the world, 45.6 millimeters a year. And this again is bounded by the Pacific plate. It's next to a strong region. The El Pilar Fault in Venezuela, again, Caribbean plate to the north, strong. Guiana Shield to the south, strong. Whoops. The Boconó Fault, same thing. Guiana Shield, not quite the same, but Guiana Shield to the south, a strong region on one side that allows this localization of deformation. Cayman Trough, strong region. Once it goes into a continental region, it splits into faults, many separate faults that are different from one another with different slip rates. The deformation spreads out. The one exception is in this area. I think I'll skip by and just say the Tarim Basin is strong, and the Altintag Fault is next to it. The Kunlun Fault, the Chaidam Basin in here is strong. The Kunlun Fault lies along it. The Tajik Depression in here is strong, and the Darwas Karakul Fault lies along it. And if I were to go on, and obviously I've gone way beyond where I want to go because I had other material I wanted to cover and I didn't get to it. So I'll stop here, and I think I will just skip to my conclusions, which I didn't complete all of. But deformation within continental regions is diffuse. Are there blocks? Well, on the one hand, of course, because there are faults, there must be blocks. But do they help us? No, they don't control deformation. Strength increases downward in the pressure-dependent brittle upper part and increases downward, decreases downward where high temperature creep makes deformation viscous. Olivine is stronger than most crustal minerals, though not pyroxene. So plate tectonics works in oceanic regions, but continuous deformation works in continents. This is, again, my strong opinion. Within the lithosphere, non-Newtonian viscosity prevails. This has strain rate varying as stress to a power, n. And so this enables localization of strain to occur, and major strike slip faults develop near strong objects. And I didn't get to this sixth one, so I won't say anything more. I'll stop here a couple of minutes before 5 o'clock your time. And if you want to ask questions, feel free to do so. I'll pick up where I left off here next week and see how far I get. Sorry that sorry I tried to say too much.
No, that is perfect. Thank you very much, Peter. Okay, questions. What is the mechanisms linked to deep earthquakes such as Bucaramanga seismic nest?
Oh boy. The simple answer is I don't know. The Bucaramanga nest is a very special place. I think it's quite different from what I've been talking about today. The earthquakes, I think, and I may be wrong, I think occur in subducted Caribbean lithosphere. So they're not different from they're not different from intermediate depth earthquakes in other subduction zones, such as under Peru or under Chile or under the Lesser Antilles. But why there's a nest of earthquakes there, oh, I don't know. There's some local process, and I don't know what it is. And I can assure you, I've thought about this for longer than most of you have. I've been puzzled by this. I studied some of those earthquakes more than 50 years ago, and I'm still puzzled. Sorry, I just don't think I can help you.
Okay. The next one is about the Norandian block and also about the escape tectonics. So the current trend is to think in blocks when there are differences in geodetic velocity vectors. In the case of this block, the Norandia block in the north of Colombia, how can this difference be explained without thinking about more blocks? Simple subduction of the Caribbean plate or collision of the Panama block would be a good explanation?
Oh boy. Well, Hector, you and I have exchanged thoughts on this. I'm not quite sure where to start. First of all, I think the North Anatolian block is not a helpful concept. I think when one looks at the GPS, the only place that you see a block like feature is in the northern part of what's often called the North Andean block. But I don't see much evidence of it because it's small enough that and not defined by enough stations. If you go all the way to the north into the region of the Magdalena River, so you're near Barranquilla, or I keep forgetting the name of the famous, beautiful city up there.
Cartagena?
Cartagena, yes. If you go into my strong impression from your data is that region moves today with the Caribbean plate. So my strong impression is that the Caribbean plate, as we see it with geodesy, extends into Colombia, well south of Cartagena, well south of Barranquilla. How far south, I don't know. So that the relationship of Panama to the rest of this is obscure, but also, in my opinion, not important. I mean, obviously, I could be wrong. You and I have discussed this a bit, and maybe we disagree. But to me, the North Andean block doesn't reach as far north as Palasun, and I don't know the names of the towns, but it's not much north of where the Magdalena River comes out of the mountains and goes into the flat area. Now, that's an opinion that I have. I'm very sure that others don't share that opinion, and as always, I could be wrong, but that's my opinion.
Okay, thank you. There is another question. Taking into account the different strengths of the lithosphere, how could we consider a fault to act? And then, can we say that the deformation occurs in both cases, but is only seismogenic in weak?
Sorry, I missed a key word in this. Could you ask that question again?
Taking into account the different strengths.
And I'll stop.
There is some noise on the background, I don't know. Taking into account the different strength of the lithosphere, how could we consider faults to act?
Let's see. Well, I think there's no question that the proper understanding of a fault is it separates two regions that undergo. Well, first of all, there's a discontinuity in the velocity field because you have slip on a fault. So it's easy to imagine that faults divide the uppermost crust into blocks. And those blocks, but the problem that I see with that description is the blocks are broken into smaller blocks, and those smaller blocks are broken still into smaller blocks, and one has too many blocks for them to be useful. Now, maybe this question is asking is a different question, and that's what happens with faults that separate blocks in the upper crust when you go down at depth. And here, this is a good question, and it's I think aimed at a problem or aimed at a state where we're quite ignorant. So in some cases, I think these faults then spread out regions of continuous deformation. For example, in Nevada, the United States, there are faults. There are many, many normal faults where blocks, basins, and ranges move with respect to one another. But those faults do not penetrate into the mantle. Those faults almost surely become just diffuse deformation in the lower crust. On the other hand, the San Andreas Fault may penetrate all the way through the crust, through the lower crust, even though there are no earthquakes in the lower crust. There may still be a fault, and that fault may enter into the mantle and be still a narrow fault. This actually is a topic I was planning to address next week regarding New Zealand, where I don't think that applies to the North Anatolian Fault, but it is a possibility. Maybe my answer should be the image that we have of faults once they're below the depths of earthquakes is very poorly defined. We don't have a good, reliable image of what is going on down at that depth. I'm concerned that I didn't fully understand the question, and hence I didn't answer it well. But that's my attempt.
Well, this is the second part of the question. And then can we say that the segmentation occurs in both cases, but is only seismogenic in weak crust?
Sorry, could you repeat that? I didn't quite understand all the words.
And then can we say that the deformation occurs in both cases, but is only seismogenic in weak crust?
Sorry. No, I wouldn't say that. There is a misconception about earthquakes and strength. Earthquakes occur because of an instability, and that instability is the stick slip, the same phenomenon. I think you can imagine having a block of wood on the floor, and if you pull on it with a spring, you'll stretch the spring until finally the block of wood will slip. And it will slip, but then it will stop. And if you continue to pull the spring, the block of wood will slip, and then it will stop, and then it will slip, and then it will stop. The stick slip phenomenon. It's the same idea as the coefficient of dynamic friction being smaller than the coefficient of static friction. Another way of saying this is the coefficient of friction depends upon the rate at which slip occurs. The higher the slip, the lower the coefficient of friction. That's the instability with stick slip. When you make the material that then you don't have that instability, so that you still have slip, but the strength hasn't changed. The strength could be higher. So the earthquakes are not telling us about strength. They're telling us where brittle faulting occurs. And the absence of earthquakes is not telling us that brittle faulting does not occur, because those faults could still be slipping, just not with earthquakes, but with the stable sliding. So the association of earthquake activity and either strength or weakness is probably a poor assumption. Earthquakes occur because of instability, not because of high stress or low strength.
Okay, Pete. Okay. There are no more questions. Thank you very
That
much.
answer. That's the
so.
one answer I have confidence in.
Okay. Thank you, Peter. Muchas gracias a todos por atender esta quinta sesión. Nos veremos dentro de una semana.
So